Hi again, everyone, and welcome back to another Math Research Live with me, Charlotte Aten. So this week I have some announcements, and then I'll get to talking about this week's topic, which is my kind of almost elementary formula for the partition numbers. So first of all, I just want to thank everyone, whether you're watching this recorded on YouTube or watching it live on Twitch. Thank you so much for all of your support and interest over the last month. It's been a little over a month now it's been about a month since I started doing this, and I really had no idea what to expect at the beginning. I mean, I had a YouTube channel for a while, like for a few years, but mostly I just posted like recordings of talks I gave, online, at seminars during the pandemic, that type of thing. But this live streaming thing has been like a big new thing for me. And in the first month, I'm very happy to report that I am now a Twitch affiliate. I have enough stuff going on Twitch to be a Twitch affiliate, which means cool things for those of you who are watching live. And also I'm at 1,000 subscribers on my new YouTube channel. Of course, my old channel is close to 2,000 subscribers, but still I want to have the new channel that's not attached to my undergrad email and all that. So thanks so much again. Please subscribe to my new YouTube channel if you haven't already. So that's where I actually post these videos. I also want to point out that so in the chat there's some new stuff. So there's this currency which it has its default name, which is channel points right now. But you can change that, and so I'm definitely going to change that to something more mathematical. I'm thinking maybe just maths, like one of them is one math, maybe, I don't know. Maybe let me know what you think. If you have an opinion or a suggestion, feel free to let me know. And also, I'm going to have some new emojis and stuff that you can use to cheer using those points. So I've been able to use this functionality now that I've been on Twitch for a minute. And so there is one already so my partner's an artist, and they made one already. I see I'm getting, hello. So yeah, cool. So yeah, there are emojis, there's some emojis now. And my partner made one that we said we would have one of the multiple hold donut, and I'm not sure if it's available yet because we just put it up like right before this, and Twitch says that it's pending. But if not today, very soon you will be able to use your currency in this channel to buy emotes that are various many hold donuts and other such mathematical things. So stay tuned for lots of those. It should be really cool. And so this is also an incentive to, another incentive to ask questions or make comments or whatever, because I believe you get points for interacting as well. You don't have to spend money. I think I also have the capacity to run ads now, but I'm going to not do that because I think that probably channel's not big enough yet. And even if it was bigger, I kind of would prefer not to have to run ads, since I hope that people will just support in other ways. Also, you don't have to go through all this stuff with Twitch. If you don't prefer, you can also just go directly to my Ko-Fi or buy me a coffee that are linked in various places and donate to me there. And it really does help because I'm using this as a supplementary source of income as I try to make the transition from being a professor at the University of Denver to being a professor at the University of Colorado at Boulder. And so it really does actually make a difference to me. It's not like just for fun or a little bit of side money. This really is supposed to be a second job for me at this point. So please do interact and support if you can. Okay, and as always, I enjoy people asking questions. It makes things a lot more fun. Okay, so let's see. Today I want to talk about this formula that I found while I was in grad school. Let me see if I can actually pull up a copy of the paper here, since I haven't actually posted that in the chat yet. I should do that now. So first I'll post a link in the chat for those of you who are following live on Twitch. some reason apostrophes don't work for me on the chat. So the paper I'll look at today, maybe I'll say I'll rework today is this thing. Let's see. Oh, I have to sign in apparently. I guess even though I'm signed in with Twitch elsewhere, I have to sign in on this thing every time, so let me do that. Oh, okay. I have to actually log in. Let me do that. That's kind of annoying. You'd think that if it can remember my credentials for streaming, that it would be able to remember my credentials for the chat, but apparently that's not the case. It's two separate things that I have to log into. All right. Well. Not sure if it's doing there. It seems like it's not. No. Well, that's pretty annoying. So, I definitely would like to be able to chat in my own chat, and apparently Twitch is not happy about me logging into my chat on here. Let's see. Is it going to be capable of doing it this time? Yeah, I think there's something wrong with that. All right. Well, anyway, I'll just show you the paper. Oh yeah. I don't have enough channel points to join my own chat. I really hope that's not a serious thing. I think the problem is that something's wrong with the two-factor verification for Twitch at the moment for some reason. So I'm just gonna ignore that, and I'll just show you the paper on the screen. I just wanted to send you a link so that you could more easily check it out yourself. So let's take a look at this. Okay, so it's a partition formula from idempotence. It's linked on my website too, so if you wanna go check out my website, you can and see that. So this is the paper, and let's see. Okay, it's being very slow about zooming in. Oh, okay. So this is the paper, and so here, I know this maybe doesn't look really pretty, but this very long formula is a formula that I found when I started grad school, and oh, and you're not able to see it yet because I haven't switched over. Okay, here, and here's the chat too. Nice. All right. So this very long formula, if I can slide over here. Yeah. Okay. So this very long formula is this thing that I found when I was in grad school. And what's so interesting about this is that this P of n is the nth partition number. So it's the number of ways that you can partition or split up n things into different parts. Maybe I can talk a little bit more about that if people are interested or have questions. But it's a very well known thing that people have studied, like what these partition numbers are. It comes up a lot in different areas, in different aspects of combinatorics and representation theory and so forth. So it's a very well known thing. It's a very well studied thing, I guess, that people have studied this a lot. But there are a lot of things that are still mysterious about these, and one of them is whether there's like a simple, in some sense, formula for them that doesn't involve sort of like an infinite, an infinite sum or some kind of limiting of some kind of endless process. If there's like a good like sort of finite or elementary formula for these numbers, and so I found a formula that is at least close to that goal in some sense. Earlier on, when I was in grad school, I ended up finding this formula. And so the only thing that's not really elementary here, the only thing that doesn't involve just like factorials, addition, multiplication, you know, the, like just summing where the index goes, you know, 1, 2, 3, and so forth. Like, the only thing that's a little bit more fancy here is that I need to sum over this set of functions, and it's a subset of the set of all functions from 1 through n, 0 through n, that basically that can be the counts for the number of parts of a given size for a partition of n. So like there's something a little bit sneaky going on here, but still it looks kind of close to one of these basic formula, you know, more basic formulas for the partition numbers. And so when I found it, I was pretty excited because I thought, oh wow, you know, maybe I discovered something really cool. And so I started showing it to people. I showed it to, you know, a few different people, and most people didn't really, you know, seem to make heads or tails of it. I showed it to some professors, some grad students, some other grad students. Didn't really, you know, people didn't really seem to, you know, make heads or tails of it. They were just like, oh, yeah, this seems like a thing, you know. And so it just happened that I didn't really interact with anyone who was like an expert on partitions in particular. So last summer, I ended up deciding to finally type this out and post it, you know, finish, you know, cleaning this up a little bit and posting it on the archive. And I won't get into all the details. Maybe I'll leave, you know, other people's lives a little bit more personal, but I ended up talking to some different people, including someone who was, you know, a very well-respected expert on partitions and related things, and he seemed to indicate that this both wasn't anything that people already knew about, that this formula was not known, and he indicated that it was a surprising thing, you know, that this is like, you know, it was, you know, impressive that there is such a formula, and it wasn't a known thing. And so I figured, okay, great, you know, so I was like really excited at this point. I was like, oh, you know, I knew it. I should have believed in myself more. I should have tried to publish this when I was in grad school. This is really cool. And so so I submitted it to one journal that was more competitive, but I thought, you know, why not? And it was rejected. And that was actually my first rejection, and so I felt very mixed about it because I was like, well, you know, this guy said that this was like really impressive, and he's like, you know, one of these guys that's like the partitions people. So like you'd think that it would be publishable even if I needed to clean up the presentation a little bit. And so you know, then I got some advice from someone else. I reached out to that guy again, but I never heard back from him, so I didn't know what that meant. Maybe he was busy, he decided he was bored of it, don't know. But he had only very positive things to say to me when we did communicate before. And so I asked somebody else, and you know, got some advice for a different place to try, tried submitting it there in basically the same form. That was also rejected. And so this is the only paper I've actually had rejected that I've submitted so far. And one other paper that I withdrew without publishing it after getting an acceptance, but this is the only one that's been rejected so far. It's been rejected twice. So what I'm thinking of doing today now is starting to rewrite this, thinking that maybe it's still worth trying to publish because I got very high encouragement for it before, but maybe it's just that I need to change the presentation, and then that will get it published somewhere. So I guess, are there any questions? Do people have any questions about my story, or want to hear any more detail about anything related to like the publishing process, or things like what are partition numbers? You're allowed to ask like what they are if you don't know what they are, or how are people feeling about this? So this is kind of my idea, is that I should try to redo this paper somehow. Yeah. Okay. What is a partition number? So, right, like why do we care about some random long formula for this thing? Okay, yeah, yeah, okay. So yeah, I will explain what partition numbers are then. Okay, so well, imagine that, you know, let's say I want to know what like P of 4 is. So this is the, okay, so like informally, this is the number of ways we can split 4 things into smaller groups. Just in the informal sense of like smaller collections, not like the mathematical object groups. So, well, in particular, we could just sort of leave it as all 4 things together. I'll maybe just do them as chunks like this, right? So it's like 4 things all together. Or you could think of it, or maybe you could think of them as 4 things all well, okay, I'll say it like this. These are going to look similar to some diagrams that people also draw, but I'm not going to, if you don't know what those are, that's fine, it doesn't matter, but these, I'm just going to do it separately. So we can kind of think of this as saying like, just like 4 is like just a whole chunk of 4. Or we could think of it as like 4 is 1 chunk of 3 and then 1. Or you could think of it as, maybe 4 is like, 4 is like 2 different chunks of 2. Or you could, well, okay, if I had just like a chunk of 1 and then a chunk of 3, I think I'm going to think of that as being the same thing. So like, in other words, I'm going to count like saying that it's 3 plus 1 and 1 plus 3 as being like the same kind of chunking of it. Like, I don't really care whether, whichever one comes first. So, so these are kind of the different ways that you could split 4. Oh, well, then there's more as well. These are, if I'm going to split it into 2 pieces, this is kind of it. If I'm going to split it into more pieces, well, I could have 2, and then I could have 1 and 1 separately. So that's like into 3 parts. Each of these is called a part, there's this part, and this part. It's 3 parts. It's a partition. And so then, or I could split it into 4 separate things. Like I could just break it apart completely and write 4 as 1 plus 1 plus 1 plus 1. Okay, and now, unless I missed one or something, I think that might be all the possible ways. Because if I have 3 parts, each of them has to have at least 1 thing, and then one of them's got to have 2, or else, okay. Yeah, I think that this is it. This is all of the ways of splitting 4 into different parts. So P of 4, unless I missed one, P of 4 should be 5. And let's see if I can actually pull up, I'll pull up for you, perhaps, the encyclopedia, and you can see the partition numbers, should be on the encyclopedia, if it will load. You'd think partition would be a common thing that's searched for here. Alright. The number of partitions of n, okay, that seems good. So I think it's starting at 0, there's like 1 partition of 0, and then 1, 2, and then 3, but then 4 gives you 5. Yeah, so this is it. Maybe there's a list? Yeah. Okay, good, I did it correctly, and I didn't make an embarrassing mistake. There are 5 ways to split 4 into different parts. And so, if you try to start doing this with bigger numbers, oh yeah, here, let me zoom in more so you can see. If you can try zooming in, or if you can try doing this with bigger numbers, you'll start to find that, well, you get lots of different ways of splitting larger and larger numbers into different parts, and there's not really any sort of like super obvious pattern. I mean, it grows, you can say things about it, but like, it's not like the next one is just like, 2 times the previous one, or n times the previous one, or something. It gets to be a lot of ways of doing it, and it doesn't necessarily follow any obvious pattern. Does that make sense as far as an explanation goes? Are there any questions about what the partition numbers are? Okay, well, just be sure to let me know. Okay, cool. Yeah, so just be sure to let me know if you think of any questions. But like I said, there are many things that are understood about this. You can go read and see all sorts of different links. There's a lot of connections and everything. I mean, it's a big area, but apparently this specific formula for those numbers is not known. Yeah, so like it's actually apparently not known whether there is a so-called elementary formula for it, and I had a little trouble totally getting people to nail down what they mean by that, but I think I can probably give a definition, but I haven't yet seen literature that is like there's research on like what types of function, like what type of function it could be, but I don't really know of any results saying that there can't be an elementary formula in the sense that it's something only involving like addition, multiplication, subtraction, summing over, just sets like 1, 2, 3, 4, and so forth. Like this is kind of close to being elementary in the manner I described before, because I need the set Vn that is kind of related to the partition numbers, and so that's like the one place where this fails to be elementary. But apparently, even something as messy looking as this is still, this at least in this particular direction, as far as I know, being someone who doesn't do partition stuff and partition number stuff every day, this is maybe the furthest in this particular direction that anyone has found such a formula. There are formulas that involve infinite series, other things, but they involve some kind of like limiting thing that's not like an elementary arithmetic thing, and so yeah, it's I mean, it is kind of surprising. You'd think that it's really a question that you could explain to a 5-year-old in some sense, like how many ways are there if I have like 4 blocks, how many ways are there of like grouping them into little groups together, and like you'd think that this is something that we would be able to come up with a formula for, but it just turns out to be quite hard apparently. Other people have spent a lot more time than me in doing various things with this, and apparently the answer is that it's quite difficult. So that's why I was so excited, because this wasn't even something that I really set out to do exactly. It was a kind of a side effect of other things I was interested in, but I was really excited when I found this, and so I felt really vindicated when after all these years I finally showed it to someone who was an expert and I got positive feedback. And so it's kind of it's made my first couple of paper rejections not sting as much, because I'm like, okay, but I was told that this was like really impressive, so like it must just be my presentation or something else. So my goal is to kind of rework this paper. And I'll start showing you how I'm going to do that. And of course, in the process, if you want to ask any questions or anything, or I guess, okay, maybe what will convince you is I should be able to plug the number 4 into this and get 5 as the result, right? Do people want to see me actually try to use the formula to compute P of 4 to convince you that it works? I've written code to check that it works, by the way. All right, yes, by hand. I will do this. I will do this by hand. I will now compute this by hand. Yeah, just to convince you that it's correct. I will now do it by hand. I will compute P of 4 using this formula. All right. Here we go. Okay. So the result that I should get is 5. Right. So I'm gonna. Well, if you want to be convinced, then yeah. So I will convince you that this is that it does actually give you 5 by computing it. All right. So according to this, okay, I need to actually make this smaller. All right, come on. Okay. I need to be able to see the formula. You know what? I'll put the formula on my screen, so I will end up writing it again, but I'll put it on my screen where I can see it, and then I will just have the whole screen, your whole screen be this one. Okay. So I will actually reproduce the formula here. So it says that P of 4 should be 1 over, so n is 4, so 4 factorial is 24. And so, so 1 over 24 times the sum. Okay, so it's the sum over g and this vn. This was the one like not elementary part. So I need to have this set, which is v4. So these are all of the functions, which I call g, from the set consisting of 1, 2, 3, 4 to, let's see, 0, 1, 2, 3, 4, such that basically that it's a valid partition count function. So let's see. So sum from, well, actually, let me not even do it that way. Let me do it in the way that makes it more evident what it is. It's all such functions with the property that if I do 0, no, there's no 0. So if I do 1 times g of 1 plus 2 times g of 2 plus 3 times g of 3 plus 4 times g of 4, then I will get 4. And so what this means is like this g of 1 should be like the number of parts that have one thing in them. This should be the number of parts that have two things in them. This should be the number of parts that have three things in them, and so forth. So like this is very closely related to the partition number. Like there's no question about it. I'm not trying to like trick you about this. Like it is closely related. So yeah. So that's also why it's not elementary, because I do need to sum over the set of such functions. But still, the fact that this relationship exists like is not. I mean, it's still not. Yeah, I mean, apparently it's not like a totally trivial thing that this relationship exists. Because like, okay, certainly, if I have such a function, you know, I mean, if I have such a function, then I could say, well, you know, why don't I just, instead of doing this, I could say, well, why don't I just sum, you know, sum over the set of all of these functions. I could just add up 1. That would be the total number of functions like this, right? And well, you know, because I don't care about the ordering of the parts, choosing like how many parts have size 3, how many parts have size 1, how many parts have size 2, and so forth. This is basically choosing the partition. So like it's clearly very closely, you know, very closely related. So I could just do that. So the reason why this is interesting is because I'm not just doing that. I'm saying that if you you know, if you take all of these functions, then each one contributes like some amount of stuff over here, and then if we average that out in some way, then we're going to get the partition number. And so like the reason that's interesting is because that gives us hope that we might be able to eliminate this condition on what we're summing over and just turn it into something that's totally elementary. So it's not supposed to be obvious how that can be done, because I don't know how it can be done, but it's conceivable. And so there's something a little more interesting going on than just saying, oh, look at the number of functions that could represent the number of parts in the partition. You know, it's there's some kind of you know, not obvious averaging thing happening here. So okay, so what is this saying? If assuming that we know what those functions are, then I need to take the product k equals 1 to 4 of, well, okay, so k minus 1 factorial to whatever this g of k is times g of k factorial. That's such a long formula. G of k factorial times some other stuff. Let's see, what is our other stuff? It's times, okay, so n is 4 minus, okay, the sum from s equals 1 to k minus 1 of sg of s. Oh, this is so long. S g of s, choose g of k, times the product of something else that is also very long. You know what? I'm gonna have to do a new page, and I'm gonna compute each of the parts. I'm gonna compute each of the parts separately, which is also how I did this when I actually coded it before, because it's too long to do it all in one line. It makes it impossible to follow what's going on. So there are a couple different parts of this that I need to compute, and so let's see. First of all, well, okay, so I guess I need, maybe I'll do the last part of this first. I need the product from v equals 1 to, so I need to do this, so this g of k for each k. No, okay, alright, I know how I'm going to split it up now. I haven't done this by hand in so long. Oh, wow. Yeah, it takes a long time to actually do the calculation of this. Alright, so what are my valid functions that are my valid functions g? Well, here, I'm going to make a table. So if I take the partition, and then, so one partition is 4 equals 4, 3 plus 1, 2 plus 1. Oh, well, I guess I can do 2 plus 2 first. 2 plus 1 plus 1. And then 1 plus 1 plus 1 plus 1. Okay. So for the corresponding function g, I have g of 1, g of 2, g of 3, and g of 4. And so I have to figure out what each of those are. So if we have one part that has size 4, then a 1 goes here, and all of these are zeros. And let's see, if I have one part that has a 3, then there's 1 3, and there's one part that has a 1, and then the rest are zeros. There's no parts of that size. If I have two 2's, then there are 2 with size 2, and then the rest are zeros. Here, if I have 1 2 and 2 1's, the rest of those are zeros. And here, if I have 4 1's, and the rest of these are zeros. Okay. So clearly, there's a very close relationship between these functions and the partition numbers. There's no getting around it, right? So like that's you know, like clearly, in order to use this formula, I mean, there's this one, you know, caveat that you have to know these functions, but finding these functions kind of amounts to finding the ways that you can split it, and so it's, you know, like it's in there. This again, there's this averaging thing, which is not maybe quite as obvious. Are there any questions about how I produce this table, though? I guess first of all. Okay. So, because of course, once I know this, the values in this table tell me how to split up 4 as some number of parts. Okay. Oh, also, if you do see, I don't know how to actually check in this interface if it's been updated yet. But if you do find that donut emoji, be sure to use it. Like, that'll be really cool if it shows up this time. But if not, we'll just have to look at it. We'll just have to take a look at it next time. Also, it is kind of crazy that I don't have currency in my. I should have like unlimited currency in my own channel. Oh, it's because I'm not logged in. That's right. All right. Well, maybe I'll take a second and try to log in again and see if Twitch is going to be any more cooperative than it was a minute ago. Just because that seems like that would be a nice thing to do. Okay, so let's see if Twitch will allow me to log into my own stream chat. Let's see. Now, did it actually send me anything? Oh, yes, I figured it out. Fantastic. Alright. Very nice. Okay. Fantastic. Oh, and you know what? I was right. I do have unlimited channel points. Let's see. Can I do the emoji? Is there a new emoji? No, not yet. Alright. There will be a new emoji from my partner's artwork very soon. I think it just hasn't propagated through the system yet. But I'm very pleased to see that I do have an endless amount of channel points. It's very nice. Alright. Well, great. So that's cool. I'm getting better and better at using all of the various functions on Twitch. Alright. And I appreciate everyone being on their best behavior while because I would have had to log in if I needed to, like, mute or ban anyone or anything. So thanks for being cool and not causing a ruckus. Okay, so here's the correspondence between the partitions of 4 and these counts, these what I call g of 1, g of 2, g of 3, and so forth. So there's really a different function g for each of the partitions. And so now for each of those functions, I have to compute something, and so let's look at the case where g of 1 is 0, g of 2 is 0, g of 3 is 0, and g of 4 is 1. I'm just going to sort of cram the 1 into the corner, as you do when you don't have enough room left. You won't give up, and so you just kind of stick it into the corner, and then no one can read it later. Not even you. You just, but you do that, and you feel like you had enough space. If you really force it, you have enough space. All right. I'm starting to realize that there's no way I'm going to actually be able to compute this by hand in the allotted amount of time, but I will do at least one piece of this to convince you that it's possible to do it, to give you the idea. Okay, so all right. So I need to compute for each such g. I need to compute the following thing. I need to find the product from k equals 1 to n, which is 4, of this factorial to the g of k power times g of k factorial times this binomial coefficient 4 minus the sum from s equals 1 to k minus 1 sg of s times, choose rather g of k, and then also times this whole other thing, which is still also part of this product. So I then need to have the product from v equals 1 to g of k of this expression 4 minus the sum from s equals 1 to k minus 1 g of s and then minus g of k minus v minus 1 times k minus 1, and then choose k minus 1. Alright, I need that. I need to compute that for each function g. So let me do it for this one first. I'll just do it for this one. The g that corresponds to the trivial one where it's just a single part that has four things in it. Well, okay. So I need to compute this, whatever this product is, for all these values of k. So let's first look at what do I get when k is equal to 1? Well, I have here a 1 minus 1, so 0 factorial is 1, and then 1 to any power is just 1. So that goes away, and then let's see, I'm going to have g of 1 factorial, so that's 0 factorial, which is 1, so that goes away. There's only one way to put 0 things into an order. It's just one way. Let's see. Then I have this binomial coefficient 4 minus this sum of these sg of s's up to k minus 1. Oh, but k, I'm going to do k equals 1, and so this is going to be an empty sum, 0. So 4 choose g of 1. So 4 choose 0. So how many ways are there to choose 0 things from 4 things? There's 1. So that's going to be 1. All right. So this whole first part is 1. Then let's look down here. We're taking the product from v equals 1 to g of k. Okay. Well, g of 1 is 0. So it's an empty product. It's an empty product. So that's going to just be 1. So that's just 1. Okay. Well, let's see what happens when k is equal to 2. So I didn't write down all the details because it would have taken forever. But okay, when k is 2, 2 minus 1 factorial. Well, it's 1 factorial, which is 1. Whatever power, it's still 1. G of 2 is 0. 0 factorial is 1. But now 4 minus. Okay, so now I'm going to go up to 2 minus 1, which is 1. So in other words, I don't want it there. I do actually pick up a binomial coefficient here. Over here. So I'm going to get 4 minus, okay, so I just need to do when s equals 1. 1 times g of 1. No, but g of 1 is 0. Okay, and then choose g of 2, which is also 0. Okay, so that's just 1. And then let's see this product. G of, okay, it's an empty product. Okay, fine, it's just 1. That one's also 1. K equals 3. Okay, for similar reasons, I see the pattern. Oh, no, I shouldn't be too hasty. Okay, so 3 minus 1. So some parts of this will be non-trivial now. So 3 minus 1 is 2 factorial is 2 to the g of 3 is 0. Oh, so 2 to the 0 is 1. Okay, so that's still 1. And then 0 factorial is still 1. But now here I'm going to end up with 4 minus 1 times g of 1, still 0. And then minus 2 times g of 2. G of 2 is still 0, so that's all zeros. 4 choose 0 is 1. And then this is still going to, okay, so this is also 1. So they're all 1. Okay. And then k equals 4. Okay, there's one last one. For k equals 4, I need to have, okay, so now it's 3 minus 1 factorial, so 6 raised to the g of 4 power, which is 1, so I finally get 6 times g of 4 is 1, 1 factorial is 1, times, okay, for similar reasons, that binomial coefficient, no, okay, so now I'm going to get something different. So for that binomial coefficient, I'm going to end up getting 4 minus 0 minus 0 minus 0, but I'm going to choose g of 4, which is 1, And then, let's see, for this product at the end, so now I have 6 times 4, and then this product at the end is going to give me, is going to give me, I'm going to do from v equals 1 to g of 4, which is 1, so for when v equals 1, let's see, if I'm plugging in v equals 1 here, well, I'm going to get 4 minus this summation, because I'm doing g of 1, g of 2, g of 3, this is going to be 0, so that's all going to go away. Minus g of 4, which is 1, so I'm going to actually subtract 1. And then v is 1, so this is going to go away. So that's all just going to become 4 minus 1. And then choose, well, k is 4 here, so choose 3. Okay, well, so at the end of the day, I get 6 times 4, and then 4 choose 3. Well, choosing 3 things from 4 is the same thing as choosing the thing that you didn't choose. And so, you know, I have 4 different ways of choosing, choosing 3 things from 4 things. So, 6 times 4 times another 4. Okay, so I get 1 for k equals 1, and 2, and 3, but I get 6 times 4 times 4 for k equals 4. Now, in order to use the formula then, I need to add those together. Yeah, believe it or not, I'm not sure if I've ever actually done this whole thing by hand before. I'm just doing it now to apparently try to convince you, but I'm at least going to do this one part since I decided to try and then realized it's too tedious. But okay, so now I'm supposed to take all of those numbers, and I'm supposed to actually let's see. So I needed to do this for each k. I needed to compute that value, and then I need to take the product of all of them. So I get 1 times 1 times, oh, that's not a multiplication. 1 times 1 times 1 times, well, okay, 6 times 16. So what, 96. Alright, so anyway, I get 96 apparently. Okay, so I need to do this for each of those g's. So remember this table. So what I just did was this one, which is like one of the easiest ones where they're all zeros, but one of them's a 1. I need to do that same thing for each of these other 5. And you'll notice I get different numbers. Yeah, I get different numbers. This one is 96, whatever that means. It's got 96 of them, and so some of the numbers will be big, and other ones will be quite small. But when you add them all up and you divide by 24, I claim, exercise left for the viewer. I claim that when you do that and you add up all the numbers that you get for the different g's, and then you divide by 24. Then by some miracle you'll get 5. I've written computer programs that verify this. Yeah. This should be the short that I should do on YouTube Shorts, or maybe start a TikTok and just go, okay, in the next 30 seconds I'm going to do this long calculation. You see, I'm going to take this formula, I'm going to plug some numbers into it, and we're going to see that it's 5. And then I'll do part of it, I'll be like, you know what, this is going to take too long, you can figure it out yourself. And I'll just put down 5, and then I'm done. That's it. I did it. Yeah, so anyway, I promise you, if you actually do this, you'll discover that it works. Okay, so apparently, yeah, so it does work, and I have actually used the computer to do a bunch of examples to convince myself that I didn't make a mistake. And so, yeah, so that's the idea of this paper. Well, okay, maybe that's not the idea, but that's the main thing. So feel free to ask me whatever you want about the calculation, but I'm done trying to do the whole thing by hand. It's too tedious. I I don't want to do the rest of it the whole time. It'll take me like another 2 hours to do the rest of the calculation, the P of 4 by hand. It's too much work. So anyway, I know I have reasons that I know that this formula is true, and again, it's kind of cheating because you have to know what those functions are. I'm just skipping through now to show you something else. Let's see. So here's just me deducing that this is true. Oh no, okay. Now I've reached the point where I'm speculating about what's going on with this. No. Oh, okay. Oh, we find that equation 1 follows. Okay. So here's where I say, unfortunately, summation makes us sum over all of these functions, and that's kind of cheating. If we could find those functions, we could just count how many of them there were, right? As we sort of iterate through, however you do it. If you find those functions, just look at how many of them you found. It was just doing the calculation. So the question was, I wrote a formula to verify it. What does that mean? It means just running the calculation. But I have a proof that is I have a proof that this works, and it's reasonably intuitive. So it's something that I've shown a number of people at this point. There's videos of me giving lectures about it to more purely mathematical or professional audience or whatever you want to call it, and no one has objected yet. I mean, people have said, I can't believe that I can't believe that no one's used this to produce this formula yet because it makes so much sense. So I think we're quite convinced of this, but no, there's no actual formally verified proof that this is a thing. In the sense of using the computer to verify it. I mean, people I think are quite convinced that this proof that this is correct. But yeah. Yeah, exactly. Because it's it's always you look back and you say, it's so easy. Why didn't people invent all of this stuff before? Why did it take us thousands and tens of hundreds of thousands of years of experience in order to reach this level? It's because it was it was all so clear. You just well, in any case, I started speculating about how to eliminate the set that we have to sum over, because that's really the tricky part of this, or the part of this that is undesirable. So I moved the n factorial over to say, okay, let's move that over, and if you sum this over the different numbers of things that you could look at their partitions, then you get this expression. And the reason why, this you might say, well, why do I want this? I'm summing over all the g's for all different n's from 1 to m or whatever. You're summing over this thing that still looks pretty much like a mess, but it kind of looks very similar to this, where you just have a function from 1, 2, 3 up to m into 0 through m. It can be anything. The problem is that this isn't giving you all possible g's. It's giving you it's not giving you all possible functions of this type. It's just a lot of them. Maybe it's some larger collection of them, and so this summation looks really pleasing for other reasons. This is perhaps something that might remind people of there's this umbral calculus, and there's these kinds of expressions are very considered very nice in some sense. And so this looks encouraging. This looks very similar to just summing over all possible functions that you could choose, but it's it's not quite there. I mean, of course, if I could make m like infinity, then I guess eventually, then I guess it would be, but that's well, yeah. I mean, I'd have to think about the limiting. I mean, it would just turn into another like description of like this, you know. It wouldn't really be elementary anymore. Then it would be you know, another one of these. It's like, oh, you take the limit of this, and then yeah. But I mean, maybe still something I'll mention. So anyway, that's basically the paper, except for the part where I show you how I got this. Do people have any questions about just like what the deal is with this entire formula at this point, or like just anything related to this? Let's see if has the donut emoji appeared yet? No, I think it's not going to this time. All right. Well, hopefully next time we'll have the donut emoji for you. But okay. So how did I do this? Or well, I guess what do people want to hear about? I can tell you just like a vague summary of how I did this. I can start actually trying to rewrite the paper. Well, okay, those are the two big choices. But in order to rewrite the paper, I have to actually figure out how I'm going to rewrite it. Like I'm going to brainstorm how I'm going to do that. Because something about this has turned people off, or whatever AI they're using to judge the paper without actually reading it. How do we feel? We have hearts full of neutrality. Okay. Well, I won't show you the actual calculation because it's tedious. Oh, and I'll give you the paper too, since I mean you could have copied it into your browser by now. But I'll actually send you the paper and the link to the integer sequence in order to let you just explore that on your own. But okay, how did I find this? Whatever this ridiculous formula is, how did I do that? Well, so what I wanted to actually count were something called idempotents. And so, in other words, I wanted to look at functions that took a set, like maybe, 1, 2, 3, through n, to itself, with the property that if you take x and plug it into f, and then you plug it into f again, you just get the same thing. That's what it means for a function to be idempotent, or idempotent, if you prefer your emphasis to be different. Well, if you think about what each of these functions looks like, so if you plug in some x, you'll get some f of x, but if you plug that into your function, you'll get f of x, the original f of x again. So this is also f of x. And if you keep doing the f, you'll just keep getting sent back to the same point. So, oh, sorry. I'm not drawing this picture correctly. Here, let me do something that's not so horribly wrong. Okay, so here's f of x, and here's my x. I'm gonna draw the picture this way. Okay, and then f of x gets sent to the same thing, and over and over. There might be some other element that also gets sent there. So the arrows are going this way. That's what I messed up before. So there might be some other elements that also get sent to the same value. And so in general, there will be a whole bunch of these that get sent to the same value that just keeps going back to itself over and over again. And then over here, there might be some other things that get sent to this value, that get sent to itself, and so on. actually, here, let me give you a concrete example of this. I'll choose one that'll be pretty interesting so that you can actually see a good example of what this is doing. So let's say that n is equal to let's say 10. Then I'm going to draw a picture of what the function f is doing. Let's say that 1, 2, and 3, let's say that they all get sent. Do I want 10? Whatever. I'm going to just draw a picture, and then I'll choose n to be whatever it needs to be in order to make my picture make sense. This is a recurring theme in math just over and over again. I'm going to just make everything the way that it needs to so that whatever it is that I said I wanted it to be will be correct, and then that solves like not all of your problems, but like 90% of your problems are solved by that. Like I'll just change the rules until the rules say that I won, and then I did it. It's like shockingly effective. Now it doesn't always work, and some people say, that's not interesting. Like that one didn't really work, but it works so much of the time. It's like just unbelievably effective. And then of course, if people tell you, well, it was easy, anyone could have done that, you say, well, why didn't you do it if it's so easy? You know. Okay. So let's see, 9, 10, 11, 12, 13, and here's 14. Okay. All right. So this diagram is supposed to represent a function, and the way it works is that if there's an arrow going from something to something else, that's what the function sends it to. So for instance, f of 3 is equal to 4, and 4 is also what f of 4 is, and it's also the same thing as f of 2, and so on and so forth. F of 12 is 14, and whatever. Right? So I guess n equals 14 here. It's 14. Okay. So are there any questions about the picture? If you like the picture and you want to get more into the picture, you can always think of these as little bouquets. And so this is like the thing that everything's getting sent to is like where the that's sort of the base of the bouquet, and then each of these numbers is like a little flower in your bouquet. All right. Now remember, I'm not the artist. My partner is, who's made some awesome graphics that hopefully will be available next week, since it hasn't come up yet. But this is my attempt to draw a bouquet, and so you can think of it's each one is like a bouquet of flowers is the idea. Now, I mean, you're allowed to think of them as other things, snakes or whatever, but I like them to be flowers. This function is idempotent. If you do it twice, you'll get the same thing, because if you're up here and you do it once, you'll get down here. You do it again, you just stay where you're stuck. You just stay at the base of the bouquet. So it's definitely idempotent. And notice that it also is basically representing a partition of the number 14 in this case, because there's 14 things. So you can think of this as like here's a part that has 4 things in it. Here's a part that has another 4 things in it. Here's a part that has 3 things in it. Here's another part that has 3 things in it. So you can think of it as a partition of. You can think of it as a partition of the number 14, but it's an idempotent function from the set with 14 things in it to itself. Okay. So why do I care about that? The reason that I care about that here, maybe let me just see if I can pull up. Pull up this paper again. The reason why I like that perspective is because there's this result, is Burnside's lemma. And so basically what Burnside's lemma is saying, it's something that you'd learn in introductory algebra or maybe graduate algebra course. So the number of orbits, if you have some group acting on a set, just some set in general, like in this case it would be, there's a natural group action on these idempotent functions, and the group action is basically you can swap the flowers in a bouquet around. Like I can switch the place that 5 and 7 have in this little bouquet here. Or you can exchange bouquets with each other, so I can either just kind of swap things around inside here, or I can exchange bouquets with each other as long as they have the same size. That's the symmetry that it has. So I can exchange the bouquets that have 4 things in them, I can exchange these bouquets that have 3 things. So there's a natural group action on this set of possible idempotents, and it acts by exchanging the bouquets with each other in the manner that I just described. That's also an example of a wreath product. If you've ever seen wreath products of groups, this is a natural example. Okay, so if you have a group action, it turns out that the number of orbits, which in our case happens to be exactly the number of partitions, it's equal to the average. Basically the average size of one of these stabilizer subgroups. And so this is a little bit of algebra that I won't really fully get into here, but unless people are really curious, and then I'll get into it as much as you want, but maybe I'll just say this is this basic result that you would learn in one of these courses, and if you apply that in this situation, I've been told I shouldn't use this I of x is for the set of idempotents. I've been told that E of x is actually a more standard notation, so I need to change that. But if you do this with this group action on the set of idempotents, then it tells you exactly that the number of partitions is 1 over n factorial times this sum, and then you just have to know what the size of these stabilizer subgroups are. And so when you do that, well, I go through here computing what the size of these stabilizer subgroups are, and this is where this formula comes from. It comes from counting the number of ways that you can, the number of symmetries that you have when you, where am I going? Okay, here. It comes from counting the number of symmetries that you have when you have some idempotent like this, and you want to keep track of the fact that you can swap the bouquets if they're the same size. You can also swap within a bouquet. Like, figuring out how many ways there are to do that for a generic such picture is what you basically what you need to count the size of the stabilizer subgroup. So one of the things that I need to do, which I don't know, but if there's an automated system or just somebody who's not paying, not looking very carefully, I don't know. I don't know what the reason is that that this has been rejected twice, but since again I got some good feedback on it, but I think I need to add more references. This I think is partly a sociological thing. I think maybe if my situation in life was different, I might not need to, or if we were living in a different era, then I might not need to, but I think it may benefit me to cite some people who are more likely to be reviewing this, or otherwise just find more connections. Like, the polite way to say it is that, like, I should explain the connection to the existing literature. The problem is that I just didn't know that when I wrote this, and I'm still not, like, a partitions person, per se. So this reference is, so it's true that I do know some connections, and like that it might be worth looking at this book on representation theory of finite monoids, but at the moment I don't really use anything from it in this paper as it is. So you liked his finite group representation theory book. I should check that out at some point. I think that I only actually have ever really gone through I'm spacing on the guy's name, and now I feel bad. The one that's like from the 70s where he wrote it for his wife because she was a chemist and he wanted to write something that was like an introduction for her to representation theory. I can't believe it. I've done like half of this book and now I'm just totally spacing on the guy's name, Serre. That was it. So Serre's like representation theory of finite groups or something like this. Oh no, it's so I know of Fulton and Harris, but I've never really read it. But it's Serre. I just was like completely spacing. So I've actually only done the first half of Serre's book. I haven't done the modular representation theory stuff from that book. But I guess that was I'm trying to remember if that was the part that his wife actually needed. I don't really remember what, I haven't looked at her chemistry work, so I don't remember what she actually used from that, but like, presumably, I don't know. I'm not sure if the first part was for her and then he went off into the modular case, or because like you'd think if she was doing stuff with like actual molecules in the real world that she'd care about their symmetry, she'd care about their actual like geometric symmetries in like real space, in like Euclidean space, but maybe somehow the modular representation theory came up there. I don't know. I don't know enough chemistry to know where else representation theory would be used besides the symmetries of crystal lattices and other such things. Anyway, so the group. Okay, so there's a question about the group. What group is acting? So the general group that's acting is. So there's a group that takes one of these idempotents and it gives you a different idempotent, a potentially different function. But sometimes you can relabel things, but you end up with the same function. So like you can obviously look in the paper and see, but like to give you a small example, it's like that isn't going to have 14 different things in it because it's too big. It's like so there's a general group action which is relabeling basically, or if you want to think of it like representation theory, it's like a conjugate representation. So like for instance, maybe I have this idempotent that sends 1 and 2 to 3. And if I change labels by sending maybe I send 1 to 2 and 2 to 3 and 3 back to 1, I do that permutation. Then if I relabel, I end up with a picture that looks like this. So I send 1 to 2, I turn 2 into 3, I turn 3 into 1. So now I have this thing, and one gets sent back to itself. So if I call this F, and I call this G, well, it's actually not the case that, F and G are not the same function, because when I, do F to 3, I get itself back, but when I do when I do G to 3, I get 1 instead, so it's not the same function. But sometimes you can do the relabeling here and say swap 1 and 2, and if you swap 1 and 2, you get a different picture. Yeah, so it's like the permutations that leave the function unchanged. And so there's two basic ways to leave the function unchanged. One is by swapping around the flowers in your bouquet just amongst themselves, and the other way is by swapping bouquets with other bouquets that are the same size. So this one only has one bouquet, so I can't do the swapping. So if you have a group acting on something like an orbit is just like like, so here's an example. It's not the Rubik's Cube group. Let me say it that way. So if you want to see an example, like the group of integers acts on the integer lattice by we can say if I do I can do this action by saying, like, if I do n, I'll do n plus I'll write my action like this. If I do n plus ab, I just mean I'm going to take a and add n and then b and add n. I'm just going to do that. And so this is an action. This is an action of this group on the set, just c squared as a set. So what does that look like? It looks like taking the integer lattice, 0, 0, 1, 0, negative 1, 0. Yeah, exactly. These diagonal lines become orbits. So like 0, 0, if I add 1, I'll get to 1, 1. Or if I add 2, I'll get to, 2, 2, and so forth. And so the orbits just end up being these diagonal lines are the orbits, because they're all the things that are reachable by adding or subtracting, an integer according to this action. Yeah. So if you're talking, so this is a representation in this is like a representation in the just like in the set theoretic sense. So if you want to think of it formally, so one way to think of this as representations is to say like, okay, I have a monoid. Maybe I'll just call it M, and it's the monoid that has an identity element and a single idempotent. I don't remember what I called it. I'll just call it A. Whatever. I don't remember what I called it in the paper right now. So that monoid. So if I have so I can think of a set theoretic representation of that monoid as just being a homomorphism from that into well, the set of functions from a set to itself. So like a representation on, I guess, x, a set of functions from x to itself. Because this is, or I guess the way that you might see it, what is the monoid that I would want here? I guess it's what you would call the t of x, the full transformation monoid, whose elements are functions. These are things that are the set are just functions from the set x to itself under the composition operation. So a set theoretic representation or a discrete representation of this monoid is just a homomorphism into the full transformation monoid on x. That's what like a set theoretic representation would be. So this is, in other words, you can think of this as being like a degenerate version of saying, okay, that makes sense. Yeah, but yeah, so like, of course, this is kind of degenerate, and like, I guess in order to maybe sell the formula a little bit harder, then like, it's natural to say like, well, what if I try to produce a similar formula, but instead of doing this, instead I say, instead of doing the full transformation monoid, I want to look at matrices, n by n matrices over your favorite field. Certainly, all of if any of these like discrete representations you would have, as long as you take n to be the size of x, you would basically have those encoded as matrices. But then you'd have lots of other ones, and then you could ask, well, like, what if I try to, what if I try to produce a similar formula using that instead? What do you mean, like a free thingy? Like, oh, like, or like that the discrete ones, the set ones are like generic, maybe. Okay, well, you're also welcome to keep your secrets in case. Um, oh yeah, well you can't. Yeah, I mean you can. So if you wanna think of a more, if you want to, okay, instead of just saying it like this, if you wanted to, you could say that I want to look at endomorphisms of, I'm just going to say the vector space on the set instead, but so take the F vector space with formal basis, the elements of the set X, consider its endomorphism monoid, I guess. These are like, you know, these are like matrices of the appropriate type, you know, and so if you say it this way, that this is like the discrete version, and this is the not continue. Sorry. Well, okay. I guess I'll say that's the discrete version, and then this is. But maybe I'll just put big square quotes. Continuous. It doesn't really have to be continuous in the sense that you could take F to be a finite field or something. But yeah, there are these as well, and so each one of the discrete ones you can view as a continuous one, over a field, just and there's like a natural way to do that, and so well it is basically because there's a functor that takes a set X to the vector space whose formal basis is X, and then you're going to have that induce a homomorphism from functions from X to itself. That's going to be included from that into endomorphisms. All right. Okay. Are there any questions now? Am I like really far off in La La Land? How many people do I have who are like totally cool with this? All right. I'm getting one thumbs up that this is okay. Yeah, so like I don't know if I actually want to try to write up like what the like finite field analog of this formula is, but at least maybe I'll speculate on it harder. So maybe I guess what I should do at this point is I should write some notes about what it is that I'm going to actually try to do if I'm going to rewrite this paper, unless there are other questions or comments, in which case I'll happily answer those. But okay, so here. Oh, no, I'm too far over. What do I need to do? Okay, so, well, one thing is discuss, whatever that means, analogous formula over field. Spell field, that would be nice. Fields, probably finite fields, just to make myself happy. Because then I don't want to have to do the actually continuous analog of it. Try taking limit of the formula for the thing that was like the sum from k equals 1 to so like m of k factorial p of k, that formula. At least talk about that. I'm not sure if it'll really come out to anything nice, but it's worth mentioning. Yeah, because it seemed. I mean, okay, it seems like it would still make sense. No, because I have to actually show that it converges. It's not like it's just gonna. It's not like it's just obviously fine. All right, so maybe that's a thing. I guess to go along with the first thing, so for better or worse, people like abstraction, and so maybe discuss some more abstract framework for such formulas. So like what I hoped would happen is that like I would get some things along these lines as my edits when I submitted the paper somewhere, and they'd be like, okay, like, you know, you wrote this when you were a grad student, you've got a bunch of details that we don't need. Okay, I'm just gonna get rid of lots of details. I don't actually. In case you don't know or you're curious, actually offering a lot of details that makes the paper very readable is actually usually harms your ability to publish the paper, unless they ask for lots of details, in which case you've got to give all the details. Usually they'll tell you if you try to put in lots of details or make it more accessible by explaining like where things came from, as opposed to just saying like it is clear that whatever, maybe giving a citation if you're feeling charitable. Having details that make the paper readable is usually going to discourage people from publishing it. I'm not really entirely sure of all the factors that resulted in this behavior. Part of it was probably that in the before time, papers were actually published on paper. And they made actual books that were journals, that were actual physical objects that you would acquire that would have the papers in them, and they don't want it to be so long because it takes more paper, and so they would want you to reduce it. Now I think it's that people don't want to they want to just skim through it and get to the good part, and they don't want all this like introductory stuff if they're more experts. But having a supplementary materials kind of thing. Definitely seems reasonable. I've heard a lot of people say, I'll just leave the version on the archive. That's the version that's, right. The version on the archive is the one that has all the details, and the version that's published is the one where they're all removed. So everyone can only access the archive version anyway, and so that's the one that they'll read. And the simplified, or the one that has all of the actually perhaps useful information about how to figure this thing out removed is the one that's published in some journal that you have to pay $100 to look at it or whatever. I definitely would like to shake my fist at 3-page typewriter papers from the 50s. It's very hard still to publish short papers. They can't be too short these days either. Like it's a hard thing to do. It is possible, but people used to. Okay, so like this is my perception anyway. I wasn't there, but it seems like back in the day, people used to like write up some stuff, and they were like, this seems quite good, seems cool, and they'd write up some stuff by hand, right? Maybe some pen, whatever, like nice enough on pieces of paper. And then they'd go to their department secretary, who was not an administrative assistant, was a secretary, right? Like that was, the whole like 1950s like kind of like secretary like deal, right? And then she would be someone who would have perhaps become a mathematician in the in the formal professional sense, and she did know how to like do the typesetting for papers, or like later on, even like when things were more computerized and there was tech, like she would actually know how to write tech, like she would be like fluent at writing tech, and you would just give her your paper or your whole book, and then you'd go, hey, thanks for typesetting this for me, let me know when you send it off to the publisher, and like you were done. Like, I mean, maybe you'd get some edits back, but like you as the mathematician, you were just done. Someone else would do all of this for you, and like put it in the envelope and send it off or whatever. Like that was like, I mean, it's just, that's my understanding of it anyway. And it's like it's just unbelievable. Like obviously I don't want to have to be that secretary. I'm happy that I can actually be a mathematician and not just somebody's assistant typing their thing up for them. But like it's you know, it's a lot of work to do that part of the job, and now we have to do it ourselves. Yeah, I mean, it's yeah, so it's a whole thing. But anyway, that's my rant about what it was like before, to my understanding. Because you'd see, like, in books, too, it's like, oh, thanks, like, so-and-so for, like, typing this entire thing in tech. Like, yeah, I mean, you know, I have the same position that all academics have about it, which is that I you know, I don't, okay, maybe not literally all, but like, you know, I don't have the power to alter the situation. I have a very, I'm here on Twitch, trying to amuse you and perhaps solicit some form of support from you, you know, in order to survive. I definitely don't have the authority to stop us from engaging in this process with people, but you know, it is a racket, you know. But don't tell any of them I said that, because if I don't publish in the list of journals that I need to publish in to get tenure, then they won't give me tenure. There's like all kinds of deals that go on so that your taxpayer money can go into the pockets of these people. Yeah, so definitely, you know. Oh, and it's going to be extra fun too, because I'm going to be working for the state of Colorado soon, because I'm going to be at a public school at CU Boulder. So yeah, your taxpayer dollars pay for me to make money for some private companies, especially if you live in Colorado. Anyway, are there any other questions that people have? You probably don't want to hear me do 20 minutes on academic publishing. Let's see. I need to discuss maybe some analogous formula, so it gives some abstraction. People like the abstraction. It gets things published, even if the original thing wouldn't have been. It's just people just want to see that there's an abstraction. Oh yeah. You're talking about like the thing about well, you know, it's like the thing with number theory, where I don't remember if it was Hardy or who it was like, oh, you know, the great thing about number theory is that it's never going to be used for war. It's just a pure, you know, intellectual exercise. It's just for its own sake, and it's beautiful and everything. But you know, of course now, you know, cryptography is a huge thing, and like number theory has like lots of like very serious, like, you know, defense related like implications. Yeah, that's true. Some sequences really do blow up pretty fast. But yeah, of course, you know, there are lots of applications. Anything to do with computing, you know, anything to do with, obviously anything that touches like artificial intelligence is like a, you know, a big thing at this point. And, like, there's always applications, and they know there's going to always be applications. So they just wait and see, you know, what comes out. Eventually there will be some application. Yeah. Well, anyway, so I need to get rid of lots of details. I need to make this abstract formula. I guess that's pretty much what I was thinking. I'll add more references. So I think I didn't do that. I do actually know of a couple more reasonable references that I just haven't added yet. So add more references. So I need to do these things. I suppose that I'll start actually trying to do this and seeing if I can start reworking this in the time that remains, unless anyone wants to see anything else in particular. I keep checking to see. Yeah, I don't think that emoji is gonna appear for me. We did one of the emojis that we said we would do on the first stream we said we would make an emoji, and it will be here at some point whenever Twitch finishes processing the image or whatever it's taking so long to do. Maybe next week you'll be able to use it. So make sure to collect those channel points. I don't think I already mentioned it in the stream. I'm not sure. I'm going to leave it as a surprise in case I haven't already mentioned it, so that you can discover what it is and be amused by it and everything. So maybe it'll be today, or maybe it won't finish processing. But it's very obviously not one of the. It's not this one. This is like the default. It's like the default one. What is this menu? Oh, I can report my own emoji. I don't want to do that. All right. So yeah, it's not. It doesn't seem to be in my interface yet though. So it's not the little hype one. Yeah. So hopefully soon it will appear, and we'll have more going forward that are all math themed and stuff. And if it gets big enough, we can do merchandise. Who knows? If I actually get enough people subscribing and stuff that it's worth doing. My partner again is an artist, so it's we definitely have a good possibility of making some cool stuff. But yeah, okay. So I guess I want to actually try. Making this paper, and so let's see. So here it is. Well, here's the default. Here's the default thing. What is this? Oh, great. Yeah, thanks so much for subscribing. I think this is the first occasion where someone has done that since I've become a Twitch affiliate. Since this is my first stream since that happened. So cool. I haven't seen the fanfare for it and yet stuff. So yeah, that's pretty cool. Thank you. Yeah. Nice. Yes, thank you for subscribing. I'm still learning many of these things, so that was a cool first experience for me. Yeah, thank you. Yeah, absolutely. Wait, so you mean you get my factors? You mean what n factorial is for different n's? Are you gonna correct me if I say that 5 factorial is 121 or something? Oh, or you just mean you're gonna tell me if I dropped an n factorial somewhere? You're gonna be like, no, that there needed to be an n factorial in the formula. Okay, or am I overthinking this joke too much? Oh, okay, yeah. Well, no one's ever been able to keep track of minus signs. Oh, okay. All right. This is a brief aside, but I'm gonna, in case you haven't seen this, I'm gonna show you something really awful that I did in my thesis, and then I will do this. So if I look at no, that's the wrong part of my thesis. So if I look at my thesis, my actual thesis, so there was this part that was on representation stability, and if you look at so it's a generalized FI module theory. If you've been exposed to any of this, I'm not going to get super into what it is, but if you take a look at my thesis, you'll discover that as you go through this part on that has to do with representation theory, there's little overlines on these guys. There's a little I forgot what the name of the accent is at this point. It's a rounded little U. There's just an unbelievable amount of little here's that little apostrophe, this little thing. There's all of these accents on all of the characters that I decided to use as part of the notation for this thing. And so I ended up having like these really like unpleasant looking expressions where like everything's got like these little decorations on them all over the place. And I would go through it and I would just be like, oh no, I missed one of the little accents and now the expression doesn't make sense anymore. Where did it go? And I think that probably in all likelihood there's still a mistake in that one of these like little decorations is missing somewhere. Oh, that's a brev. It's not the pointy one. It's the rounded one. So in case that jogs your memory better. But I don't know. But okay, so brev perhaps. So I mean the odds are they're nested too. They're nested. So there's overlines over expressions that have the brev or whatever it is inside of them. Brev, I don't know. But as you can see, it really. Let me see if I get. Oh yeah, and then I have the little like this one that's like more like that's more like Scandinavian. That's like in like Angstrom or whatever, and it's just and then I do use the letter C throughout just to make sure that it's even more difficult to actually read any of it. Let's see if I can find where the actual like the longer calculation. Okay, so yeah, I mean we have these guys. That's fine. Let's see, there's some longer calculation. I mean, no, the calculations aren't actually that bad per se. I mean, once you know the notation, but just like I'm like learning this notation is just like I've lost it again now. Like I can figure it out, of course, but like it's just oh yeah, alpha's got like 4 indices. This was not my best work when it came. Oh, and then there's dots now too. I forgot. There's also dots. So like that's something else apparently. Oh, actually, I remember what. No, what were the dots? No. I remember the dots. I remember what the dots were. I think. Anyway, yeah, it's just this was not my best work when it came to notation, like at all. This is just a series of really questionable choices. Anyway, I'm done with that now. I think. The actual math, I think was good. It's just, yeah, everything is different. That's true. It's like one of these things that happens where you're like you want to talk about things categorically, and then you're like, well, technically, these two things aren't the same, but they're very similar. I don't really want a whole new like symbol for it, but if I use the same symbol, maybe I'll get confused, so I'll do this accent, and then once you start going down that road, you have like 6 accents, and you're like, it's just, I don't know. There's no really good solution to it, because like sometimes you have to say it's obvious how to interpret, this, like things like, oh, this is just a set, but this is a set with a trivial group action, like, that they're really not literally the same, but they're similar, and yeah, I mean, it's just, there's no real right solution. This is also why I feel kind of ambivalent about like actually formalizing everything, like, because I kind of feel like, well, it's true that you can always have like make sure that things are interoperable, that you like have translations from like one system into another system, or one formalism into another formalism. It kind of feels like the actual content of the mathematics is like the ideas, and that like you're not really, if you try to find like your perfect formal basis for everything, then you're like not really, you're kind of like maybe getting rid of that in exchange for like something that you think is like the Uber thing, but it's just your thing, and then later you realize it doesn't work for somebody else's thing, and it's just, I don't know. I have some reservations. Oh yeah, different fonts. Yeah, that's the other path that I haven't gone down as hard. So I do math cal, like the calligraphic ones, um, and the blackboard, of course. But I've never the fractor writing. I've never really done as much. I'm not as into like Lie theory anyway, which is really like the area that does it a lot. Um, but yeah, I mean you can go really intense with the fonts. Oh yeah, I mean that's the whole thing, really. Basically, I mean you do need to have the actual proof and like the actual result to be sure that it's correct, But like it's never really about it's not really about the theorem. It's about the method of proof, and even the method of proof, it's not really about the um, you know that specific proof itself. It's about the type of idea or technique that let you prove the thing. And so, it's always like in one step above, and like the real thing is that you had an actual idea at some point that you can communicate to another human being. Oh yeah, I do use the script. I do use scripts as well. That's true. I actually write those by hand sometimes I'll do it for categories a lot. Categories will be math script. Yeah, that's true. Yeah, I think I'm going to avoid diacritics in the future. It's yeah, it's not an ideal thing. All right, let's see if I can copy paste a bunch of stuff into here and get it to work. Oh, okay, did that for me automatically. Cross-references. Oh. What cross-references do you want? Oh, everything's fine now. Okay. Oh, because I didn't make title. I won't have too many more things that I post on the archive that will still say University of Denver on them. So first of all, I'm definitely going to have to redo the abstract. Oh, I want to make my little I have my little thing that lets me do comments with my little color that I do. Okay, let me see if I can find where that is, and then I'll pop back over here. See if I can get it from this other thing. This is the real trick to writing tech or doing anything like this, writing code. It's a lot of copying and pasting the same stuff that you already did before. Now, of course, you can fall into the trap of copying and pasting stuff that other people did before. But the problem is that if you don't actually understand it, then you're not going to have a good time. And many people have been doomed by random forums or Stack Overflow, or now language models, thinking that you can just copy other people's stuff verbatim without actually understanding it and expecting to have a good time, because people post all kinds of stuff on the internet, and lots of people think that they're right about something and they're wrong. You've really got to be able to vet things for yourself. Okay, that's not Oh, I put the redo. Oh, yes, I want to redo the whole paper, but I meant for this to be in the abstract. I need to write a new abstract based on however I change those. Alright, so I need to redo the abstract. Let's see what parts of the old thing I do want to carry along. Well, I guess I'll leave the name the same. Let's see. Okay, this does say the correct year for the math subject classification. I used to have to change that manually, but I guess 2020 is updated. Oh yeah, no, CoCalc is pretty similar in terms of its like overall functionality. It's way cheaper. Like Overleaf, a year for like the like paid Overleaf where you can do like more than 2 people on a private article is like $150 right now or something for an individual. I don't have like an institutional membership. But for CoCalc, like a low tier, virtual machine is like $50 a year, and so it's like a third of the price, and like the functionality seems quite similar. I think you may even be able to have an unlimited number of people on the free tier of documents that are private. Don't quote me on that, but I think that you can. It's just that you're running off of whatever the like excess like residual computing resources are that are around from what the company purchases, and so like it's probably not going to be as fast, but certainly if you pay, if you're looking at the paid tiers of these things, then CoCalc is, I think, definitely the way to go. So I'm hoping to transition collaborators off of Overleaf as time goes on, and eventually just be totally on CoCalc, and then I can stop paying for Overleaf. And anyway, CoCalc is like it's like the people who do Sage, the computer algebra system. It's open source. I believe CoCalc itself is actually open source. It's a good thing. I do still use Overleaf as well at the moment, though. Let's see. So I think a big problem with this, maybe, I'm really not sure, because the thing is, like, when you get rejections in math, also the thing is that like they don't have to tell you why they rejected your paper, like, at all. You can literally, so okay, you're not supposed to, but because you don't have to give a reason, you can literally see a paper by someone that you don't like or that you don't agree with politically or whatever you think is, competition for your thing or whatever. You can say, I'm an expert in this, and I don't permit that person to publish a paper because it's obviously not any good or something. You don't even have to explain yourself. Like, you can just say, like, I don't care for this. It's whatever. Or at least that's my understanding of it. I've been given the impression, at least, that you don't have to actually have a real reason at all. I mean, I'm sure that probably my paper was not rejected for such a fancy reason, because I think that probably people just don't even know who I am, so I don't think they're discriminating against me. I guess I'm not hiding my name, but that's not really realistic for me to do, since I'm a pretty known person on the internet. Anyone who chose to look me up, as people often do, I think, when they're reviewing papers, can know that I'm a woman, for instance. You know what really annoyed me is so speaking of the comment about Overleaf, like anything mismatched, it gives you the red like error thing immediately, and it gives you anxiety. I had this thing where like I had like valid. It might even have been from a draft of this paper, actually. Let me see if I can find let me see if I can find it in here. So I had a command. Maybe it was in this paper. I'm not sure. Let's see. It wasn't this set command. No, it was a different paper. I had a command where like it was no, I think it was this, actually. I do think it was this. It was this. This absolute value right here. Here, let me maybe even see if I can zoom in a little bit more. Alright. So this is an absolute value command. It just makes the vertical bars be scaled to the size of the input, so if you put something really big in the absolute values, then it will, it'll stretch them appropriately. But this has right in it, like left and right in it, and these are things from math mode. So fine, right? It's supposed to be used in math mode. It's a command that belongs in math mode. And I don't understand why I can't provide command and then have something that, there is no reason that I can't do this. It works. It's correct tech. But Overleaf insisted that this was wrong. It would always give me the red highlighting over here and say you can't do this because it belongs in math mode, but this isn't math mode. It's but this command will be issued inside of math mode. It's half the commands that you're going to write are going to be issued in math mode, if not more. But I don't know, for some reason Overleaf just couldn't handle that. So there's a lot of little things like this where it's if this platform did this, I am paying for this, but also it's open source, it's a lot it's a lot smaller of a thing. Be okay, fine, but it's open source, and if I really cared so much, maybe I'd try to fix it myself, or I'm not paying that much money for it, whatever, right? But when Overleaf does stuff like that, it's I'm paying, oh yeah, I can file an issue. And when Overleaf does stuff like that, I'm paying so much more money for this thing, and okay, for instance, they took years to implement a basic dictionary functionality, and the dictionary on Overleaf still doesn't have usual mathematical terms in them. I'll get the most ridiculously unrelated suggestions when trying to type in combinatorics or I don't know, quasi-group or whatever. It'll just give me the most unrelated things, and it's people use tech to write math. Maybe also linguistics, things in computer science, whatever, but it's math, right? This is who it was made for. And it just seems unreasonable, that the dictionary functionality is like that. And I can't I couldn't, at least I couldn't, I don't know if I can now, import my own dictionary. I think I can't duplicate dictionaries and Overleaf from one project to another one, the custom dictionary. It's again, if I wasn't paying so much, then I wouldn't really care as much. Also, I just realized that my video is kind of small here. Let me see if I can fix that. Oh, there we go. Well, anyway, yeah. It seems unreasonable that it should be like that. But that's the nature of the thing, right? As long as people are paying for it, then it's good enough, and it survives. Yeah, but I'm quite happy. I'm quite happy with this so far. Let's see. So, oh yeah, I was going to illustrate too. So, one problem with this that is definitely a problem, that, it's not just me speculating about people persecuting each other when, when reviewing papers, which again, I don't think really happened to me. So this first sentence is me bragging because after I discovered that this was something that people would maybe really be interested in, I felt really full of myself, and I felt really good, and I was okay, I want to really brag about the fact that I found this early on in grad school, and it's actually not, it's not something that I did at the end of my time in grad school or anything. I found it right away, and I think that that made me feel good about myself at the time to be bragging. I think that when people look at that, they say, well, it better be really, really good. Because if it's not, then you shouldn't be bragging about it, and then, if it's not, if it doesn't, absolutely blow my mind, then I'm going to think, this person thinks they're so great, they did this thing in grad school, whatever, I did things in grad school, too. And so I think that maybe I won't actually include that, and again, I expected them to just say, you should remove this, but I'll have to, I'm going to actually change this, and so I'm not going to lie, of course, but I think that in order to have a better chance of publishing, I have to act as though this was the result of some long and arduous investigation of something that was much more arcane than what it actually was. lest the reader be lulled into believing that they could possibly ever understand this. So this has all got to go. This is definitely a problem. I need this to like strike terror into people's hearts, or else I won't be able to publish it. All right. So, which I guess if any of that's accurate, that means that my other work must already do that. Yeah. Yeah, I think I'm just going to drop the commentary since I've told enough people in the world about how I did this when I was in grad school, and I feel satisfied with that at this point. But yeah, it's definitely got to be super categorical. Like I'm gonna have to describe something as occurring functorially, even though it's completely unnecessary to do so and actually makes it harder to understand. Yeah, that's gotta happen at some point. I don't want to get too wild with it because people. I mean, I do truly believe that people have some ability to figure out if you're messing with them. But it's. Yeah, I mean, I do probably need to be fancier in order to publish it. Yeah, but it's unfortunate that the world is like that. But I mean, that's what it is. Let's see, what am I looking for here? All right, so I have this. So what do I actually want to keep? I guess is the question. Yeah, I don't know if I want this discussion to change. Well, okay. Let's see. So I guess I'll just give the core thing of it first. Okay, so is this the introduction? Some kind of introduction. Here's this paragraph. Okay, so instead of making this like really the main thing, now the main thing is going to be some much more like general formula that's just saying basically the exact same thing that I did here. But instead, so now I'm gonna present what is the actual like main result perhaps as a consequence of the main results. So I'm gonna just present this as a trivial consequence of the main results of the paper, which is just going to be just some just from the perspective of someone who has written this, it is an obvious generalization that is not necessary to understanding the formula, but I'm going to introduce it and use fancier language and see if it alters the reception that this receives. I think believe it or not, I think I've actually never seen the, what would you call it, the verbal noun of corollary before. Corollarization, that's nice, that's good. Yeah. So as an obvious corollary of the main result, we have this. Okay. Looks like it's rendering okay, which is good. All right. So I'm going to need to rewrite. I'm going to need to present that as a consequence of the main result. Okay, like here's an example where like we have like this dot is highlighted. This period in the sentence is highlighted red because CoCalc doesn't like it for some reason. But like you have to punctuate your sentences even if they end in display math. That's just how the world is. Okay. So there's some more introduction, but I'm just going to ignore that. Let's see. Oh, there's some monoid representation preliminaries. Let's see. What do I actually want? this. Yeah, I think I need to. Just redo this. Actually, I don't need like most of this. Okay, so the corollarization is a functor from the category of propositions to the product category of theorems and corollaries. Yeah, that seems good. I'm going to resist the temptation to actually produce a formal explanation of that, because I believe that you could probably okay, well, so here's the thing. I think that okay, no, I'm gonna resist. I'm not gonna be nerd sniped by this. You can definitely consider categories whose objects you can think of as being as propositions, and whose morphisms are the implication, and you can interpret what you said in terms of that, but I'm not going to do that right now, because that's going to get me, that's going to be the entire rest of the stream if I try to actually go down that rabbit hole. No, I mean, you're welcome to try to derail, but I have to try. I mean, I don't have to do anything I want, but I would like to try to stay focused on what I'm supposed to be doing according to whatever I decided at the beginning. But yeah, so okay, so I have this formula. So I need to totally redo the derivation of this formula in a way that removes like as much possible intuition as I can. And so that's going to be like a pretty large reorganization. Okay, so what I'm going to do is I'm gonna definitely plan to have a section. Like how would I do this today if I was just trying to do it more cleanly? I have the introduction. Maybe I'd just say monoid representations and conjugation. Okay, and so I'll describe in general that if you have representations of a monoid, there's a conjugation action. Let me think about this. Okay, because like I guess the question is what is the theorem? So if I'm gonna say, all right, so you can look at representations of a monoid on some set or in some vector space or whatever, then you have this conjugation action. So you have a group action, and you can count the number of orbits by averaging over the sizes of these stabilizer subgroups. But that's Burnside's lemma. So I guess what more specifically am I saying? It's Burnside's lemma plus I guess if it happens that so I did this in the specific case where I was looking at idempotents, and so I was looking at representations of this specific monoid. So I guess I maybe really do want to prove a more general result. Maybe it's not really like a totally pointless abstraction, because otherwise I can't just say the general result can't just be apply Burnside's lemma to this. That's not a theorem. That's not a theorem. That's just just do this well-known thing. Cyber lemma. So I guess I really do need to say because it's noticing this is an interesting thing, but like if I'm going to generalize, like what's the appropriate generalization? Well, I guess I really do need to think about what that would be, because like if I want to state it as a theorem, I definitely need to have an appropriate generalization. That's like not, I can't really just say apply Burnside's lemma to this situation. Alright, so let's see. Because like, I guess computing the size of the isotropy groups was like, you know, not so like, you know, computing the size of the isotropy groups was like not entirely trivial, but like, you know, it still is something to do. Yeah, I guess I really do need to think about this. I was being more flippant at first, but I suppose if this formula isn't interesting enough on its own, well, I guess I have two options. I can either do a generalization that is like a kind of pointless generalization in the sense that it's not like what the original motivation was, and I can generalize it to I can generalize it in some direction that I know that I could do in principle, but it seems like more work. Or I guess I could explore the consequences, but I feel like exploring the consequences is harder for me because I'm not as much of an expert on partitions already, and so trying to mess around with that is going to be more work. So I think I am going to try to generalize the setup. I'm just annoyed because I do feel like this is actually going to start to take more effort than just trivially. If I want to state a theorem, it's going to be more effort than just trivially stating the general situation here. So the general situation is like you can consider applying Burnside's lemma to this this kind of representation. All right, fine. So what I did in the original paper that was so much work was I gave like a gentle introduction to the ideas here. The fact that idempotents are the same thing as choosing an image and choosing which things go to which things in the image. We have an action by conjugation. Oh, let me actually make it so that you can see all this better. We have an action by conjugation, and like I verified that this actually. I verified that this actually was a group action. See, this is a prime example of something that can't be included because like I just have to say that's obvious. I mean, I guess it is once you know it, because everything is. But like, all right. And then I have idempotents here. Find conjugate idempotents. Let's see. I gave this isomorphism, but that isomorphism, like this is definitely trivial for sure. It's basically saying like you don't need to worry about the identity element when you're considering this conjugation action, because like if you have a representation of a monoid, then the identity has to go to the identity of the thing that you're representing in, and so there's only one choice, and it doesn't affect it doesn't really mean it doesn't matter. You can just ignore the identity. So that's definitely trivial. Let's see, what is this? So I mean, this is something that would be an observation and not a proposition, probably, and something that was like a more serious paper. Okay. So then here I describe the actual structure of this wreath product, but I think what I'm going to need to do is I'm going to actually just there's a little bit of detail to figure out here about like which way you want the action to go or whatever. like there's a couple different like reasonable conventions, and so yeah, so I think like that result that the stabilizer is this product, that's just going to be stated as something obvious. Okay, so let me try to make some notes in my new version of this. Okay, so I'm going to just very briefly, I'm just going to make some notes for what to actually do for myself later. I'm just going to define monoid representation, and conjugate representations. If I could spell representation, that would be good. Define monoid representation and conjugate representations. Give notation for the group. Well, give notation for well, yeah, I guess for the group acting by conjugation. Okay, so I'll give some notation for that group, and then okay, and then I need to discuss the stabilizer. If I could spell stabilizer, that would also be good. Stabilizer subgroups for well, maybe I shouldn't discuss the stabilizer subgroups here. It said I'd just give notation for that. I need to define the representation and conjugate representations. In set and linear cases. I'll say some stuff about the field with one element to really drive it home that I know what I'm talking about, because I know about the field with one element. All right, I'm not going to write that down though, because that's too flippant to be an actual note to myself. This is making me wonder about something. I don't need another new thing to actually do, which the goal was just because the sheer number of publications matters in terms of like getting jobs and like getting tenure and all of that. Like the actual number of publications matters, and so I just want to increase the number because I already had this, and this seems like it was actually a good thing according to some guy who apparently would know about that. My goal is to get a paper out of this with the minimum amount of additional work necessary as possible. So I am tempted to actually describe the corresponding formula in the linear case, but I'm also a little bit hesitant because that may actually require some amount of intellectual effort to produce a reasonable formula. But of course, if I did for finite fields, then I could actually try taking the limit as q goes to 1 and seeing if it gives me the formula that I was already looking at, which probably it will, because that's how life is. But, which I don't think is necessarily really that interesting beyond the formula itself, but who knows. Yeah, I also suspect that yeah, it's not going to be well. Yeah, I think that this is possible to do using like the Q binomial coefficients to say something about like I would guess that it's possible to do a finite field analog of this. That's like actual work. Does anyone have any idea what I'm talking about at this point? Like what's going on with you guys? I'm like debating with myself here, like how much additional effort I want to put into this thing. I need some generalization or something that I can say is a theorem that's not just the formula itself. Do people know what I mean by the finite field version of this? Okay. So I'm gonna describe to you. I'm gonna describe to you what the I'm gonna go to new page 2. Yeah. What is the transition from the discrete case to the vector space one? So I'm still doing the representations of this monoid. I guess little a is my idempotent element. Oh. E is the identity. So okay, so a like set representation. Oh, pretend that says representation is a monoid homomorphism from M into this transformation monoid. So a field representation would be a homomorphism from this into, there are different ways of saying this, but like one way is to say, so an n-dimensional field representation of this monoid would be a homomorphism from M into the monoid consisting of n by n matrices over the field. It's not like a group representation. It's not into like GLN. It's just matrices, which are not necessarily invertible. So, of course, if you have a set representation, right? Like maybe, I mean, whatever row of E is, it's just in the case of the set representation, it's always just going to be the identity function for X. Whereas for the field representation, row of E is always going to just be the identity matrix. All ones on the diagonal, zeros everywhere. Right? It's just the identity, the n by n identity matrix. So the only really interesting thing is what row of A is, and so in the discrete case, it's just a idempotent function. Some idempotent function f, say from x to itself, and then row of A here is going to be some idempotent matrix. I don't know, maybe I'll call it big A, why not? So this is going to be some n by n matrix over the field, where A squared is just A. So like if I have a set representation, I can always make it into a representation over any field. And in some sense that, it shows up in lots of places, the set version of things is like the field version of things, but it's like for the field with one element. So there is no like field with one element in like the traditional like proper sense, but a lot of formulas that work for vector spaces over finite fields, when you take the limit as the size of the field goes to 1, you'll get a formula that is the formula for the set version of the thing. Does that make sense? At least like what the setup is for the vector space one versus the set one. Is there an intuition for the limit? Yeah, so it's like so the classic thing. Okay, so let me. I I guess okay. Let me do this. Let me do this as an example. Okay, so if I have I want to say this. So if I have the vector space like fq squared, or if the q bothers you, I'll do fp squared. So the finite field with p elements, and I look at pairs of things from that. So how many lines are so maybe I'll say like so how many lines through the origin are there? How many possible lines through the origin are there? Well, if you think about it, if you choose any point, there's p squared points, so the points are pairs of numbers from fp. There's p squared points, so well, at first you have p squared possible choices for the first point, except you don't really, because you can't choose the origin, right? You can't choose 0, 0 because 0, 0 doesn't determine a line. So you're not allowed to choose that one, but you can choose any of the other ones. And but then you have p squared minus 1 choices for that. But then a bunch of the choices you made will give you the same line, right? Like I can't choose 0, 0, but if I choose like if I choose like 1, 2, it's going to give me the same line as if I chose like 2, 4 or whatever, right? So a bunch of my choices will give me the same line, and so what do I need to do? Well, every possible choice that I had, every possible line really has it has p minus 1 of these other points on it, right? Like I can't choose the origin. This is supposed to be 0, 0, not infinity. I can't choose the origin, but there's p minus 1 other points on each of the lines, or just points that aren't the origin on each of the lines. So I've counted each of the lines more than, I've counted each of the lines p minus 1 times. So I overcounted. And so, so then, well, if I do, p plus 1 times p minus 1, I'll get p squared minus 1. So there's p plus 1 lines through the origin. Okay. So there's that many lines through the origin in fp squared, some prime p. On the other hand, you gotta have the vertical, right? You have to have the vertical one as well. So it turns out the way I just counted here is the way that generalizes better to higher dimensions when you change the 2 to a bigger number, and you ask instead of how many lines, how many planes or whatever. Yeah, this way of counting is the one that this idea is the one that generalizes more easily. But then, okay, asking how many lines through the origin, there's also another silly kind of question you can ask, which is if I have a set that has 2 elements, I don't know, alpha and beta, you can ask an analogous question. 2-element set is like a 2-dimensional vector space. How many single elements in this set? Okay, this one is silly, but this is like 2 choose 1, right? Which is 2. Okay, and so the point is that this is like the p, like the prime p analog of this, because if I look at the if I look at 2, that's the limit as p goes to 1 of, p plus 1. And that's not a coincidence. It's so this quantity is what's sometimes called like this is like 2 choose 1 p. This is like the, or it's usually the variable q is used instead. It's the q analog of the binomial coefficient. And so in general, what happens is that this isn't a coincidence just because the numbers are small. In general, it's like there's such a thing as like n choose k. Pretend that's the letter k. I can't write the letter k any other way. There's this, which is like the number of k dimensional subspaces of fqn, and then it's like the limit as q goes to 1 of n choose k. Q is actually like the actual binomial coefficient. And so like a lot of the combinatorial formulas that you have just for like sets and subsets and so forth, like there's like a finite field analog of those things, and if you take the limit as the size of the field goes to 1, you get the discrete formula that was like the set version of the formula. And so this kind of thing happens a lot. It's like a field with one element phenomenon is what it's called. Yeah. So like this is actually like a very legitimate thing that people study. There's a lot of puns too, because people will write like f, like like it's like the like one in French, like but it's like it's like fun, it's the field with one element, or people also just call it like f1. So like there's I haven't looked like way deep into this, but there's like I remember that there were people interested in coming up with like a formal explanation, because like I'm not, as I've mentioned before on the stream, I'm not an algebraic geometer by any stretch of the imagination, but I believe that the goal was kind of like they wanted to be able to do like set theory or combinatorics or whatever. By like I think they wanted to think about sets as being like vector spaces over the field with one element, so that they could like understand the instead of having like these two separate cases, that they can understand what's going on in terms of just the theory of having like, what am I trying to say? It's like the idea that like, because they study like algebraic sets, algebraic varieties over finite fields, and use tools that are analogous to tools from the theory of manifolds over finite fields instead. And then I guess if you could do like just sets, treat sets in the same way, then you could think about like, okay, these are really like what's a manifold over the field with one element, and presumably that would be very interesting, given that there's like these various limits that all agree with each other and everything. I don't know a lot of detail. There are some nice introductory papers, I think. I just haven't ever gotten that far into it, other than just knowing that this is a thing. So like sets are vector space. An n element set is a vector space over the field with one element of dimension n. Like this, like F1n is basically just that. This is the basis. This is the basis. Oh yeah, did that make it? Yeah, did that make it make more sense? No, this isn't literally a vector space, because like there's no zero vector. Yeah, it's like one element in every direction. There's just a little problem that there's no zero. There's no zero vector. Yeah. Yep. So that's a thing. So now I could ask instead. Okay. Well, I guess then I could look at I could look at idempotent matrices over FQ or FP whatever instead, and then I could say, okay, well, there's conjugate representations here as well, but instead of the relabeling by permutations, I would want to relabel by the elements of the general linear group, and it's it's possible. Like it's possible to write down a similar formula, but will that be general enough? I don't know. I'm also not really sure of what the actual what I'll actually be counting when I do that, since I'm not really sure what that is going to look like. Yeah, I'm not really sure. Like, here, let me attempt to actually do what I advertised and do math research live at you. um, well, let's say that if we have set representations on a set that is consists of, no, I shouldn't call it A because I called A was the other thing. I'll say x1 and x2. Right? What are the idempotents here? Well, like, because basically it comes down to like what are these idempotents, and so well, let's see. Here's x1, here's x2. I'll call the first one f. So, well, I could send everything to x1. It's definitely idempotent. I'll call the next one g. I could send everything to x2. That seems good. Or I could send everything to itself, which is also known as the identity. And I think for two spots, these are all that's possible, right? Either one of them gets sent into the other one, and that goes, or that goes to itself, or they both just go to themselves. These are my only choices. So that's it's not very exciting, but there's more going on. If instead I do I don't know, let's say f3. I don't really want to do f2. I mean, I guess 2 isn't a prime. In case you haven't been told, 2 is just not a prime number. There's too many weird things about 2, so it's not allowed. I don't have any even primes going on. It's just going to make our lives, it's going to deceive us and make us think that things are easy, and then they're not. Yeah, no, nobody likes 2. Spanish. It's canceled. See, even my dog knows that 2 isn't a prime number. He's not having it. Like, he won't have anything to do with that. Yeah, it is the oddest prime. It's really bizarre. All right. Well, let's consider representations on f3 squared. So I can identify. So I can identify x1 with the first basis element. So I'm gonna think of x1 as being like 1, 0, and x2 as being like 0, 1. And so, all right. Well, instead of that f thing that we had, instead of f, we can think about, maybe I'll just call it A. It's this matrix. X1 gets sent to x1. X2 gets sent to x1. That's this, and you can indeed verify that a squared is a. G goes to b, so everything gets sent to x2. That's like that. Okay, and then let's see. the identity, well, that gets sent to the identity matrix, which is this. Okay. So all of those are examples of, a possible choice for an F3 representation, but there are probably other examples as well. And in fact, because the dimension is low, I can probably describe what they look like. So, okay, so maybe I'll reuse the name A, and I'll reuse some other symbols as well. There are maybe more abstract ways to see this, but let's just do it. Let's just do it concretely and see what happens. So, if A squared has to be equal to A, oh, the determinant doesn't have to be 0, because the identity doesn't have determinant 0. It has determinant 1. Oh, well. Yeah, so let's see. Oh, it's all good. Yeah, it's, right. Well, yeah, because, okay, so the reason why, if the determinant was not 0, then the matrix would be invertible. A squared equals A means that you can cancel a factor of A on both sides, and then it would be that A is the identity matrix. So if A is invertible, it has to be the identity. So then the determinant must be 0, because, otherwise it would have to be the identity. So we know the one that has the non-zero determinant. But A squared, right? Well, A squared is BC, and then let's see. AB plus BD, and then AC plus BC, and then BC plus D squared. Alright, so assuming I didn't make some terrible arithmetic mistake, looks like that's what we have. And so what do we want? Well, we want that A is A squared plus BC, and then we want that B is equal to B times okay, yeah. No, please do let me know. Please do. I also can multiply, and please do let me know if I make an arithmetic mistake, since I'm actually doing arithmetic live. The band that I can multiply, I swear. I definitely know how to do arithmetic for sure. Oh, AC/DC. Oh, I didn't even. No. I guess I'm not that rock and roll. I didn't get the AC/DC thing. So B is okay. So B is supposed to be the same thing as B times A plus D. And then let's see. C is supposed to be the same thing as C times A plus B. And let's see. D is supposed to be the same thing as D squared plus BC. Okay. Well, there's a whole bunch of these guys. I just want to give you at least another example of one. Also, I guess it's worth noting, but maybe not shocking, whenever you do this, you always get some kind of algebraic set. And if I did know algebraic geometry, I might have more such things to say to you about that, but okay. Alright, so let's just try to find some non-trivial example over the field of 3 elements. Oh, actually, to make our lives even easier, we're in F3, and so if I square something, that's just right. Like if I square 0, I get 0. Square 1, I get 1. And if I square 2, I also get 1. So it looks like if I have anything that's if I just have anything that's not 0, and I square it, I'll get itself. So let's just assume that everyone's non-zero. It's just, and like this is you know, Fermat's little theorem, right? That if I'll just get one just to make my life easier. So let's just say all the coefficients are non-zero. Let's suppose that we can do that, right? So then I'll square A and I'll get 1, it's BC. Well, I guess if B is non-zero, I can cancel and I can say 1 is equal to A plus D. 1 is equal to A plus B. D squared is 1, so D is equal to 1 plus BC. Oh, okay. And so then I find out A has to be equal to D, and oh, okay, but then if A is equal to D, that means that A plus D is 1, so A is 1, A and D are both 1/2. 1/2 exists in F3, and it's the same thing as 2 because, right? Because if I multiply 2 by 2, then I'll get 1, and so that 2 is also 1/2. So A has to actually be equal to D, has to actually be equal to 2, and so let's see if that's possible. Well, B is equal to A. Let's see, B is equal to A minus 1. So B is equal to A minus 1, so B has to be equal to 1. If B is equal to 1, that means that 2 is equal to 1 plus C. Okay, so C is equal to 1. So does that actually work? Let's see. A and D are 2, and B and C are 1. And let's double check. I love you too, sweetie. And so let's double check. So 2 squared is 1, and then 1 times 1 is 1. So I add those together and I get 2. Let's see, 2 times 1 is 2 plus 2 is 1, and then 1, 2, 2, 1, so 2 plus 2 is 1, and then 1 plus 2 squared is 1 is 2. Yes, this works. There is at least one non-trivial example in the sense that this one wasn't one of the ones that came from a discrete representation. So this is a different one. And so now that we have this, we can now ask what orbit is this in? Does this belong to one of the orbits of the ones that came from the set representations under conjugation? Like for instance, I can say, okay, well, I'm going to want to, I'm going to want to conjugate it by some invertible matrix over F3. And are you okay, sweetheart?
He just got me.
Oh yeah, you're just playing a little.
He didn't want to go in the room with me. He didn't want to come out here. He looked at me. He clearly wanted some attention.
Okay.
Out here.
Yeah.
I'm sorry. Do you wanna?
But see if he'll
Show him to your pupil.
Hey, Delphi, do you want to go? You say hi to people. I don't. Please don't throw the toy to me. I'm afraid that. Okay. You know, it'll be fine. I'm almost gonna wrap up here.
Sorry, I wasn't trying to interrupt your stream. He just really wanted some attention. I'll be quiet.
No, it's all right. Okay. So yeah. So now the natural question is this? Can I conjugate this? Can I take some other matrix? I don't know, C, right, and do C inverse. C, and is it possible that I could ever choose a C so that this is conjugate to, well, it's not the one that has determinant. It's not the one that has determinant 1 for sure because the determinant of this is 0. So is it possible though that this is conjugate to that maybe? Like, can I, is that possible? Let's see. Can anyone else hear me? Am I just being too quiet? I don't think I turned the sound off or anything. Oh, okay. Huh. I'm sorry that the sound is cutting out on your end. But yeah, it sounds like people can hear me, and I haven't changed anything. So Oh, okay, good. Yeah. So, like, could this possibly be conjugate to this? Well, you know, the general linear group lets me do a whole bunch of things, and so, notice that, okay, this isn't the zero transformation, so its image is at least one-dimensional, and its image definitely isn't two-dimensional because the determinant is zero, and so it's not part of the general linear group. It's not invertible, and so if I find what the image of this is, then I certainly can change basis, which is all that conjugating amounts to, right? I can certainly change basis and take that image to just the first standard basis element, and so yeah, I think that these are conjugate. So it looks like that these are conjugate to each other. Yeah, so like there's actually, if you think about what that reasoning means, it looks like actually, unless I'm mistaken, yeah, we do have a different number of orbits for sure. So orbits that used to be separate, right? Oh no, actually I shouldn't say that. So these two, no, right? These two are already conjugate to each other. Okay, fine. So, but I think it is. I think it is possible that two things. I don't have an example off the top of my head, but I think it's possible that two things that were not conjugate. Yeah, exactly. So I think though it's possible that two things that were not conjugate in the discrete setting will become conjugate in the linear one. I think that that's possible. And so because of that, the count, whatever this analogous thing would be counting, would not be the same. Yeah, I think that that's what's going to go on here. I think that I gave an example that was a little small to be able to see it, but I believe that is actually what occurs. So it's not. I think on the basis of that it's not just gonna count the number of permutations. I think that it's not an entirely obvious generalization to just say let's do the linear version of this instead. So yeah, I don't know. I think since it's getting a little bit close to the end, I think I want to say that I'm going to need to think a little bit about what I want to do with this. I may actually just try to. I think. Oh, I see. We're doing a 5 reveal the details with. So I think in this case we're just kind of. I think we're kind of restricted based on, like, if the question is about, like, when do things that were different in the discrete case become conjugate in the linear case, I think that it's more like having a higher dimension would make it easier to see. I think that just increasing the order of the field, I think this one turns out to be not super interesting because it's two-dimensional. So if you have to have some, oh, there's a mosquito. Oh my god. All right, I have to defend myself. Okay. All right, it's okay. Just come on. All right. Oh, gross. Oh my god. Oh, terrible. Okay. Anyway, I'm safe. I'm fine. I wasn't destroyed by the mosquito or anything. We do have some huge spiders around here, but I guess they can't eat all the mosquitoes. So I have to decide. Am I going to proceed with what I've been thinking here, which is add some generalization? I'm starting to feel like it's not a pointless generalization. I was being a little bit like, I'll just add in some nonsense. If it's really a good result, then if I just change my presentation and my language, then it will be accepted somewhere and my numbers will go up and everything. I'm now not so sure about that because, I mean, like, I guess it is a cool formula, it is a cool result, but this is starting to feel like if I want to embellish it, that I have to actually do work. And people maybe aren't just going to let me get away with just finding this cool formula. They're going to try to make me do even more work in order to be able to publish it. So I might have to do more work, or I could decide to try to collaborate with someone else to possibly, put some of this work onto another person. And then I would have to share credit for the formula, but the longer I sit with this formula and it not being published or doing as much of material value to me, the more I don't feel like I need to have my special individual credit for it anymore, because I just want it to go on and be published and continue on its way without me. I mean, I'll check in on it sometimes, but like it doesn't, I don't need to, I don't need to have it be my own thing forever. So I could consider actually doing something like this with a collaborator. Or actually, now that I've posted all of this on the internet, I could just sit around and not do anything and see if someone scoops me on it later and then denies that they ever heard of me doing this exact thing that I'm describing right now. So that's also a possibility. Yeah. And, yeah, but, don't get any ideas. No, it would, yeah, I really don't want people to do that to me, but it would really blow my mind if I actually live streamed something like this, and then people were like, I'm gonna steal that, and I bet I can publish it before she can. Yeah, you should dig up notes that you made in grad school. There's probably a lot of good stuff in there. Yeah, that's right. Oh, you came up with a partition formula that came from idempotenz. Yeah, I mean, anyone could just go on the internet and said that they thought of it. It's like Gauss. Gauss, I think it was like he saw some stuff about non-Euclidean geometry, and then he went to his drawer and he pulled he was like ancient, and he pulled out some notes out of this drawer, and he was like, 35 years ago, I wrote this entire discussion of this, and I proved all of these results, and then I never published it because I thought that it was nonsense and nobody cared. And there's some version of that I think is true. And yeah, you can just lie and say that you already knew it. I mean, there's a reasonable finite amount of stuff that you could have done in grad school though. So eventually, you have to start pretending that you did it when you were a postdoc or whatever. Yeah. Oh, can you imagine what it's like to be the people at Overleaf or something, or just who people have really good access to archive or whatever, and you can just run train a language model on everyone's live teching that they're doing of their papers, and then just be like, hey, what's the latest stuff that people are into, what's coming out, and then you you just check it out, and well, so I think that actually having the thing do math in the sense of producing interesting original things by itself is very, very unlikely to take place. It's just not going to happen. Because language models can't handle doing that, but with babysitting, it's a really good search tool, so you can scoop people really effectively. If you're already proficient in the area, you just need to have private access to the private documents of the people who are actually working on a paper in your area right now, and then you can take it from them. And if you're more well known than them already, no one's going to believe them over you. So you just win. Hey, buddy. Do you want to commit an academic misconduct? Is that why you're over here? Are you going to use your institutional resources to publish before me? Oh, no, he's a good boy. He wouldn't do that. He's a good little guy. He's got his little pink ascot. He's a good one. Okay, it does look like, yeah, to a dog, I'll help you. Yeah, absolutely. Oh yeah, I mean, I'm sure that, like, there's going to be more emails from people who have proven the Riemann hypothesis than ever before, and now they finally don't need those academics, trying to keep all the secrets to themselves because they've paid to use, a language model, and computers are that's what it is. Computers are very smart, and the smart computer says that that's definitely a valid proof of the Riemann hypothesis. I mean, that's all you need. It's perfect. You don't even have to do any arithmetic anymore. Okay, well, I guess that's enough sarcasm for now. Is there any last thing that anyone wants to say or ask or anything? Yeah, best of luck. Best of luck with that endeavor. Yes, you can plug the thing into the calculator, but can you make it actually make sense with what it computes? Yeah, it was great fun. Yeah, fun. The field is one element. Great fun. Absolutely. Well, yeah, it's been really awesome, and I'll have something totally different for you next week, probably. I'm really looking forward to it, and again, I really appreciate all of your support. And hopefully, we'll even have that cool new emoji next time, and it'll be lots of fun. So I'll see you then. All right. Oh, thank you. Yeah, it'll be the most general result ever. I'll have proven some very general thing, I'm sure. Yeah, absolutely hype, and more emojis coming soon, I promise. All right, bye everyone.